Sorry we're off to a late start. I had some technical problems with my previous stream, and so this is kind of a redo of the previous one. So in this video, this is geared towards my C programming students, and this is about function pointers in C. And so I want to start with kind of a brief overview of what a function ultimately is, and then see how we can use this idea of having a pointer to a function in a program. So the first thing you should be clear on is that a function is just a block of code. I mean, ultimately, it's not, we should probably divorce ourselves from the terminology of a function and just say somewhere in memory there's a block of code and we assign it a name so that we can call it. And actually this harkens back to the old assembly programming days where in assembly language, once you compiled your program out of C or C++, or even wrote it straight in assembly, you would put little labels in your code to say, like, this is where the loop starts, or this is where my main starts. And each one of those labels basically is assigned an address. So when you refer to the name of the label, you're actually talking about the address of where that label lives in memory and what, the address of the instruction that that label is pointing to. So the same thing happens in C. When you just refer to a function by its name, you're actually talking about a label for some instruction in memory. And that's what I'm trying to do with this, show you with this box over here. So this box represents a series of instructions to carry out. It could be assembly language instructions. We might as well say that they're C language instructions. And the very first one here, the very first one to be executed, is basically the address of the function. So when we say we want to call a function, let's say we call the function, I don't know, print or something like that, what we're saying is jump to the address that print resides at, and then it starts executing the instructions here. So just like with arrays in C, if you just use the name of the function, you're actually getting its address. In other words, if you just use the name without any parentheses to indicate that you're calling the function, then you just get its address. And I said it's the same as in arrays. With arrays, if you just give it the name of the array without any of the brackets or stars or pointer arithmetic, then you're just talking about the address of the array. So the same thing happens with both arrays and functions. So here's an example of a function, a simple function. It's called foo. It takes in an integer parameter and returns an integer. And so just the name foo by itself is the address of foo. You can also put the ampersand in front of it to get the address of foo, but you don't have to. And again, this is just like arrays. With an array, you can put the ampersand in front and get the address of the array, or leave it off and you still get the address of the array. So it's up to you whether or not you want to put the ampersand on there. I'm going to leave it off because I think it makes things a little bit simpler. So what we usually want to do is we want to get the address of that function and assign it to a variable so that we can use that other variable to call the function. This is where things look a little strange. Actually, it's not that strange if you tear apart the syntax of this thing. Take a look at this here, which is the declaration for a variable that will point to the foo function. And compare it with the original one here. You can see that most of the pieces are there that are the same. Like the int out in front, that's still the same. And the parameters inside, that's still the same as well. The only difference here is out in front. The bar here is the name of the variable. This is the variable we're going to be assigning the pointer to. And the star in front is used to say, well, this thing is a pointer, right? Just like with any other variable. If I said like char star x, it means that x is a character pointer. The reason why we have these parentheses out in front is because, well, without them, the compiler would interpret this declaration as we've got a function called bar that returns an int pointer. But that's not what we want. We want it to return an int, and bar itself is a pointer. So we have to put the parentheses on there to group those two together so that the star goes with the bar, not with the int. Okay? Otherwise, it actually looks just like any other function declaration. The only difference is the star with the parentheses on there. Everything else is the same. But because this is a variable, we can assign it to the address of foo. So what we're doing here is saying that bar is going to point to the function foo. And in order to call that function, all we have to do is say bar of 3. In other words, the way we call the function, remember here was the original way to do it, right? The way you call the function using the pointer variable is exactly the same as calling the function itself with its original name. And the reason for that is essentially we have this here. Here again is our block of code. Foo was our the name that we had pointing to this block of code. Actually, the reality is that foo itself was also a function pointer. So was bar. And so foo and bar are both now pointing to the same thing. And because they're pointing to the same thing in the same way, we can use the same syntax to call them. We can say foo of 3 or bar of 3. They point to the same thing, and so they work exactly the same way. In other words, foo and bar are aliases for each other. And at this point, they more or less become indistinguishable to the compiler. It's just a name that happens to point to a block of code. All right, let's take a look at some actual code itself. Here is a simple program. I've got the same foo function here. It takes in an int parameter and returns an int. And all it does is it prints out the value of the parameter being passed to it, and it returns the value of that parameter plus 5. So if I call foo of 3, it should print out 3 and then return 8. And that's what I try doing here in main, is I call, actually I'm going to call bar of 3. Remember, foo and bar are going to point to the same thing. I'm going to assign that to a variable called z, and then I'm going to print out the variable z. So calling bar of 3 should print out the 3, and then printing out the return value should print out the 8. Okay, so on my screen I should see 3 and then 8. And then here's my declaration of the bar variable and assignment to the address of foo. Okay, so let's try compiling it. Got no compiler errors. And if we run it, we see we get 3 and 8. Okay, so just to recap there, bar is a pointer to the foo function. And when I call bar, I call it just like I would have called foo of 3. No need to put a star in front to dereference it. That happens automatically for you by the compiler. So once you get a pointer to a function, it is indistinguishable as far as the compiler goes from the original function, so you just call it the same way. Okay, so why is all of this useful? Well, let's take a look at a simple sorting program. And if you've studied sort programs before, you'll recognize this one instantly as a sorting algorithm called bubble sort. And the way it works is it cycles through the array and it compares successive pairs of entries. So the first time through this array, it's going to compare the 8 and the 4, the two out in front. And if they're in the wrong order, it's going to swap them. And that's what these three statements here do. Is this is a sort of idiomatic way to swap two elements of the array. You take one of the elements and make a copy of it over in a temporary variable, then reverse the other two, and then use that temporary one and put it back. So it's kind of a three-way triangle or cycle to get the two variables swapped. Okay, so it's going to compare the 8 and the 4, see if they're in the right or the wrong order. If they're in the wrong order, it swaps them, and then it's going to look at the next two. And if those are in the wrong order, it swaps them. Then it looks at the next two, and the next two, and the next two, and so forth, all the way down the line. And then one pass through the array is going to result in the highest value bubbling up, if you will, to the end of the array. And then we start the whole thing over again. So we end up making, let's see, this is a 9-element array. We end up making 9 passes through the array. And then each time we look at 8 pairs of numbers, and we swap them if they're out of order. And then if we do that 9 times, or actually 9 times 8, 72 times, then we'll end up with the array sorted. And I know bubble sort is an extremely inefficient way to sort, and there's probably a few, definitely are some optimizations we could do to make this a little bit faster. But the reason why I like bubble sort is that it's really simple to write code for. It's just 2 loops, and then a conditional check, and then a swap in the middle there. Okay? So I know we could do something like heap sort, or merge sort, or selection sort, insertion sort, quick sort, but bubble sort is easy to illustrate. Okay, so let's compile this and run it. And if it works correctly, we see that the array is now sorted. Oh, that's the last thing we do in the program here is we just run through the array, print out all the values. So we see that the original values were 8, 4, 0, -3, 1, 8, 2, 6, 3. And when we print it out, we get it -3, 0, 1, 2, 3, 4, 6, 8, 8. So it has sorted them and printed them out in the correct order. Okay. So let's see. What I want to do is, the first thing I guess I should do is see if I can isolate the sorting from the main, right? Right now I've got the sort embedded in the main. So how would I isolate the sort so that it works by itself? Well, of course I would copy out this section and put it up here. So this would be like void, what should we call it? qsort, bubble sort. Okay, and I'll figure out what parameters to pass in just a moment here. Okay, and so here's the guts of the sorting. Okay, so as far as the function itself, what bsort needs is it needs the name of the function, or actually it needs what the address of the function, sorry, not the function, the address of the array. It needs to know how many elements are in the array, and I think that's it. So let's say int pointer arr, let's just call it A for array, and then int size, okay, or let's call it length, like that. Okay, so we're going to go from 0 to the length. This should be the length minus 1, and that looks good. Oh, and this is going to be A, and A. Okay. So then here I should be able to say bsort array 9. Okay, so we're gonna sort the array, and there's 9 elements. Hey, sorry you have another class to go to, so go ahead and watch the replay later. Should be posted about 20 minutes or so after the video ends, hopefully by about 10 o'clock or so, my time. So that's in about half an hour when it ends. All right, let's see if this works. Okay, so let's save it. Oh, it compiled. I was actually a little worried there that it might not compile. And yes, it seems to have worked. Okay, so what we did is we took the guts of the sorting algorithm and we put it into its own function called bsort for bubble sort. We pass in the address of the array, how long it is, and then the sorting function takes over and it does the sort. All right. So that's fine and dandy, but I really want to make this sorting function a lot more generic. Right now it only works on integers. How can I make it work on strings? Well, let's change this. Actually, let's just comment that out, and let's make a new array. Let's go character. Let's see. It's going to be an array of strings, so that would be an array of character pointers. Yeah. Character pointer arr array equals, and then let's put in, I don't know, names of fruits: banana, apple, grape. What are some other fruits? Peach. I'm blanking out on fruit names here. Kiwi. These are all fruits that are kind of common to Americans. Maybe you can suggest some others here. Guava. One more. Oh heck, I'll just put melon. Okay. And then I want to say sort this, and then we'll print it out. I'm going to use S here. All right. So I've got my array of strings, and I'm going to call bsort on the array. And there, oh, how many are there? 1, 2, 3, 4, 5, 6. There's 7. So I got to change this number. Oh, I got to change that number. This obviously should be like constants or something like that. Okay, so what do I have to change here? Well, I got to say that this is no longer a integer pointer. The address of, so this is going to be like character, and since it's an array of strings, so it's an array of character pointers, this is going to be a double pointer, right? This is going to be an array of character pointers. And there's the length. That's fine, that's fine. And then this has to change right here. This is a comparison function, or a comparison operator. So it's not going to work, obviously, with my being passed in basically an array of pointers. What I have to use is string compare. And I have to say if that is greater than 0, so string compare returns a negative number if the first argument comes before the second argument. It returns a 0 if they're the same, and it returns a positive number if the first argument comes after the second argument. Okay, and then I need to include string.h. Okay, and then the swapping part, that's exactly the same. All we're doing, instead of swapping numbers around, is we're now just swapping addresses around. So all the strings are still living in memory separately, and we're just swapping around the addresses that are pointing to those strings. Okay, I think that's okay. So let's try compiling it again. Oh, that's because my swapping function, although I said it was the same, it's not quite the same. This is character pointer. Yeah, temp. Yeah, I think that's right. Yeah, got the type right. Okay, so temp is a character pointer. So temp is a string, or a pointer to a string. And yeah, that looks good. So now sort me, and look at that. It's in order. Apple, banana, grape, guava, kiwi, melon, peach. So it's in the correct order. Okay, so you see what we did here to make bsort work with strings is we had to change this type here. We had to change the way we do the comparison. So instead of a less than or greater than, we had to use something like string compare to compare strings. And then we also had to change this type right here. Other than that, the sort was fairly straightforward, not a whole lot changed, just a few types here and there. So what do we have to do to make bsort totally generic, right? So that it will work with anything. So in fact, so we could take my bsort algorithm and we could like compile it and we could give it to someone else and we could say, here, this works. You won't have to change anything in it. It'll work with anything. And so what we have to do is there is a type in C called void pointer. A void pointer is basically a generic pointer. It's a pointer to something, but we're not saying specifically what it is. It's just, yeah, it's just an address. So we just say it's a void pointer. And then the same thing here. Well, let me figure this out. Is it going to be void pointer or void pointer pointer? Let me think about this here. Because what you can't say is that, you know, void temp. That doesn't work. That doesn't work as a type. So I think we're going to have to say this is a void pointer pointer. Let me consult with my notes. Hold on here. No, I don't think so. I think we're okay to say this is so basically it's an address of somethings. Sorry, it's an array of somethings, and this is just an address to it, an address of it. So what do we do here? I guess what we've got to do say is, well, should I draw a picture? This is where I didn't quite think this far through my live stream here, so I'm kind of winging it. So what we can't do is we can't just say void temp, right? Because what's happened there is the compiler says, I don't know how much space to set aside for the value of temp. However, if temp was a void pointer, that would work. I am going to have to draw a picture, so let me switch over here. Okay, so let's say this is my array, and let's say inside of here I've got numbers like 5, 8, 2, -1, 3, 6, 8, 7. Okay, and then A is a pointer to the first element of it. And that's the A from inside of my qsort function. And so what I'm going to do is I'm going to say I've got temp, and I want temp to point to one of these things. All right, so that means void pointer temp is the address of one of the elements in the array. Yep. Okay. And then what I need to next thing I need to do is I need to swap those two of those things. So I guess that works. No, sorry, I'm staring at myself here. No, I'm not staring. I'm staring off into space because all I've got at this point is just a pointer to that, but I actually kind of need to make a copy of that somehow. You know what I need to do? What I need to do is, see, the whole problem here is that I need to make a copy of this thing, but I don't know how big it is. I don't know how big it is so that the compiler knows how much space to set aside. I mean, this could be an integer, it could be a character, it could be a struct holding 100 things, right? So the problem is I don't know how much space to set aside here. So I think what I have to do is, in addition to passing in the address of the array and how many elements are in the array, I also need to tell it how big each one of these things are so that my sorting function can set aside enough space for it. All right, so here I need to pass in like another thing, size. That's why I wanted to, whoops, let me switch screens again here. Size. I'm passing in, this is the size of each one of the elements. And so I'm going to need this temp, and I want to set aside enough space to be able to store a copy of something. So here I'm going to use malloc to do that. So I'm going to go void pointer temp equals malloc size. Okay, so this is going to be my temporary variable, and I only need one of them in order to do this. Even though inside of my loop here it looks like I'm making many temps, I only need one of them around, and I'll just recycle it over and over again. Okay, so I do this set aside size bytes, and then I got to remember to do a free afterwards. And then here, I need to make a copy of that thing. And so I think I'll use something like memcopy in order to make a copy of something. And I got to look up how to do that. I don't remember how memcopy works. Memcopy. So you give it destination, you give it the source, and you give it how big it is. Okay. So mem copy. What was that? Destination? That would be temp. Source would be the address of a sub j. And how big is it? Size. Okay. And then we'll swap those two around, and then we'll have to do another memcopy. Actually, let's just do 3 mem copies. Address of a sub j plus 1 and size, and then a third mem copy. Address of a sub j plus 1, temp, which is already a pointer, and size. Okay, and we'll get rid of these. So the reason why we have to use memcopy is because our totally generic sorting function doesn't know ahead of time how big each one of the elements are. So it's just using a generic memcopy, memory copy function in order to copy the appropriate number of bytes around. Okay, I think that's okay. So that means when I call this, I also need to pass in size of character pointer. So because each one of the elements of my array is a character pointer. So I have to pass in that. Okay, so at this point, all I'm trying to do is totally genericize it, but I still know I'm using this in the context of sorting some strings. So that means I can still use string comparison, but string compare doesn't know that these are strings. Right now, all it knows is that they're void pointers. They're things that point to nothing. So what I have to do is I have to cast these to character pointer, right, in order to force them to be the right thing. And then I have to dereference them. So that looks a little strange there. But these are the shenanigans we got to go through to make the types work out. Okay, so we're going to take one of these generic void pointer things, void things, cast them as a character pointer, and then dereference them so that we get their actual values. And then string compare should be happy now. Now it thinks that each one of these things is a character pointer. Is that right? Dereference that? No. Let's see. So if I take a character pointer and I dereference it, I get a character, but string compare expects character pointers. So this is a character pointer. I think that's right. Well, let's see what happens. It's not going to work. Yeah, there we go. Operator type void, where pointer type. Yeah, let's make this void pointer. Ha! Passing argument A here. Yeah, okay. Oh, I see. It's saying that this and this, oh, I see. So when we do this, what we have to do is we have to cast this to a void pointer, right? So we have to say, even though we know in main that ARR is an array of character pointers, as far as qsort is concerned, it doesn't care what it is. It's just a pointer to something. All right, that's got to change. All right, see how this works. Oh, no. Address of? Address of? Oh, compiled. Oh my gosh. Let's see if this is going to work. Okay, if this works, then we can move on to the next step. If it doesn't work, I might move on to the next step anyway and hope that you kind of got the idea. All right, I'm just kind of, did it work? Oh, no. I got the types all lined up, but it didn't work. So I'm kind of debating here whether to just move on and show you the next thing and hope that you kind of got the idea that what I'm trying to do here is create a totally generic sorting function. It just takes in an array of somethings. It allocates, this should work just fine. I wonder where it actually crashed. Like, did it crash into mem copies, or did it crash into string compare, or what? Let's see. So we take the element. See, like, why doesn't this work? That's not going to work. Yeah, that didn't work. Okay, so each one of the elements is actually a character pointer, but qsort doesn't know that. It thinks they're just voids. So if I take the address of each one, say that they're actually pointers to character pointers, and then dereference them, I should get character pointers out of each one. Yeah, that should be fine. I mean, it looks bizarre, but that should be fine. And then I do this mem copy here. Maybe I have to say this. Okay, those are all errors on my mem copies. Passing void to parameter. Okay, so let's just say these are void pointers. Right, we're throwing void pointer all over the place in order to like totally genericize everything here. I should have rehearsed this first. Oh, let's see. How do we do? Oh, now we got to throw in a whole bunch of parentheses. Ah. So I'm getting the value out of there. Oh, I wonder if I have to pull the same trick that I did with the other one, which was like get the address of it, cast it as a void pointer, and dereference it. Okay, if this doesn't work, I'm gonna move on, because you're gonna look at this going, oh my gosh, I have to do all of that in order to make this work. And I'm gonna say, no, you don't really, because someone smarter than us actually figured this all out many years ago. Doesn't work. Okay, forget it. This is where I was going. If I had actually gotten this to work, this is where I was going with this, is this comparison function here, right, only happens to work for strings. What if we want to make it work on other stuff? Like, what if we were passing in a struct that had information about people in there and we wanted to sort them by age? Or if we were passing in, let's say, doubles, right? So this comparison function here would change. And so what we have to do is pass into our sorting function a function that tells the sort function how to do the comparison. You see, that comparison of two elements of an array is fundamental to sorting it. At some point, actually many different points, when you're sorting an array, you've got to compare two of the elements and decide, do they go this way or do they go this way? And so all of these sorting functions, no matter whether it's the sorting functions built into the C language or the ones built into other programming languages, typically you have to pass in a function that tells the sorter how to compare two of the elements. And so let's just scrap all this here, right? Sorry about that. I wish I had gotten that to work. Okay, but there is a function called qsort. It's built into the standard library of C, and it works just like I described. You pass in an array of some sort, its length, how big each one of the elements is, and a pointer to a function that tells it how to compare two of the elements. And let me make sure I got yes, I got the arguments correct. Okay, so it's the number of items, the size of each item, and then a function that tells it how to compare. And the way that the compare function works is actually, probably not coincidentally, exactly the way that string compare works. Right, so remember, string compare, let me give you this over here. So string compare returns a negative number, so a comma b. String compare a comma b returns negative if a comes before b. Not a is strictly less than b, but a comes before b. And it returns 0 if a is equal to b. In other words, they're the same string. And it returns a positive number if a comes after b. So for example, if I was to do a string compare of banana and apple, this would yield a positive number because banana comes after apple. Okay, so this function that you're using to compare two elements needs to behave in this certain way. It needs to return a negative number. It doesn't matter what negative number it is, as long as it's negative. It returns a negative number if they're in the correct order. It returns a 0 if they're the same, and returns a positive if they're in the opposite order. Okay, so let's switch over here. So we're calling qsort here, and then we're going to pass in a function. In this case, we're going to use string compare because it behaves exactly the same, exactly the way we want it to behave. Okay, let's compile this. Okay, what did we, oh, let's see. Incompatible pointer types passing into parameter of type, yeah, okay, What's wrong? Okay, actually, I think what we have to do is if we look at, let's do this, man qsort. If you look at the manual, it says to call qsort, you have to pass in a pointer to the base of the array, the number of elements, the size of each element, and then this function here that takes in two parameters, a pointer, and it returns an int. Okay, that's actually the way string compare works. It takes in two pointers to strings, and it returns an int, and that's what it is. I think what we have to do is, we got to do this. So let's go int, let's call it compare. And we'll say it's void pointer A, void pointer B. And then we're going to return string compare. Okay, but now the problem is that string compare expects two strings, and we're being passed two void pointers. So what we got to do is we got to take A, and we have to cast it as a character pointer, and then dereference it. You should remember that little, or recognize that little pattern of casting it and dereferencing it from our attempt to make a generic qsort function. And that's why this signature, that's where ultimately I was leading with that whole thing. Character pointer B. Okay, I hope that's going to work. And then let's put in compare here. Oh, come on, compile. Oh, didn't work. All right, why didn't that work? So, oh, we need the, that's right, address compare, return int, compare. Yeah. Looks good to me. Let me look at my notes here. Oh, the function prototype insists that it be declared const. There we go. All right, They're in the correct order. Apple, banana, grape, guava, kiwi, melon, peach. Okay, so look here. So you call qsort, you pass in the array, but you have to cast it as void pointer because qsort expects a void pointer. You pass it the number of elements, the size of each element, and then the address of a comparison function. And the comparison function has to be declared like this. Int, here's the name of it. The name of it doesn't matter. You can call it whatever you want, but I called it compare. Const void pointer A, const void pointer B, and then inside of the comparison function, you call the actual comparison you want to do. In this case, it's string compare, but string compare expects two strings, two character pointers, and we're being passed two void pointers. So actually, what qsort does is it passes in the address of two of the elements. The address of two of the elements, not two of the elements themselves, but the addresses of two of the elements. And so if we have our, let's go back to our picture over here. This one here, let me do a little bit of erasing. All right, not that one. So let's say, let's call this ARR. So let's say this is A and this is B here. So we're being passed in the address of A and the address of B, so the address of the 2 and the address of 6. So we're not being passed the 2 and the 6 directly, we're being passed the addresses of the 2 and the 6, which means that A here is actually an int pointer and B is an int pointer. Right? So if we actually wanted to compare A to B, we would have to dereference both of these. So we would go if star A is greater than star B. That's what we would do in our comparison, right? But that's for integers. Imagine that's string compare. But the problem is that the qsort function passes in void pointers, not integer pointers. So what we have to do, if I could do a little erasing here, is we have to say A is an int pointer, and then we dereference it. So we cast it as int pointer, what it's supposed to be, and then dereference it. Same thing for B over here. Okay? So whatever you're trying to compare, in this case integers, you're going to be passed in a pointer to those things. Now in the case of strings, we're going to be passed in pointers to strings, which means we're going to be passed in pointers to character pointers. Each one of these elements here is a character pointer, and we're going to be given the addresses of them. So we're going to have to say if star character pointer A is greater than, and then, remember we're actually going to use string compare here, but I'm trying to show you the parallels here. Character pointer B, oops, it's in the wrong spot, B. Okay, but we're actually going to use string compare instead of the greater than, but this dereferencing is what I'm trying to get at. So we switch back over here. So we cast each one of these things as a character pointer, and then we dereference them. And then we can pass it off to the actual comparison we want to do. Okay? Let's see, I guess I want to show you one more example, and then that is to say, let's say what we have an array of, let's say, people. So I got struct person. Let's say it's character pointer name and int age. So, oops, struct person pointer array. No, actually, ARR is an array of persons equals, and then I got to remember how to do structures. I guess it goes like, how does this work? Oh, let's go Bob, comma, 18, Amy, comma 30, Pam, comma, is that right? 26, and whoops, let's do one more person. Fred, comma 15. All right, is that right? Bob, Amy, Pam, Fred. Okay, and then I want to sort them, and I want to print out. I want to print out their names and ages. Dot name and ARR sub I dot age. And there's only 4 of them this time. 4, 4. Here's my struct person. Okay, so qsort, quicksort. The array, there's 4 elements. Size of struct person, so each one of the elements is a struct person, and we're going to call our comparison function. And then here we're going to say return. Actually, we'll just do this. We'll go if, remember I got to return a negative number, a 0, or a positive number. So if struct person pointer a, actually let's do it like this. Let's go struct person pointer AA equals, I'm trying to get this right here, struct person pointer. Let's see, each one of these things is going to be a pointer to a struct person. So like that. Yeah, struct person pointer. Okay, I think that's right. And then struct person pointer BB equal, whoops, too many stars there, equals person pointer. So I'm just doing this so that I can take care of some of the casts, so it doesn't get too ugly down here. Take care of some of the casts so that cleans it up a bit. So if staring at this here, so if, oh sorry, AA pointer age is greater than BB pointer age less than, we'll go return -1. Else, if AA pointer age is equal to BB pointer age, return 0, else return 1. Remember, we just have to return a negative number, a 0, or a positive number. Oh, it compiled. And then we go, whoops, sort me. There we go. 15, 18, 26, 30. So it sorted them by age. And it kept the names with the ages, right? So Fred is still 15. Yep, Bob is 8. Yep, good, good, good. So it sorted these people by age. And so let's look here. What I did was, so the comparison function didn't, the declaration didn't change. What I did was I just said, okay, A is going to be a pointer to a struct person, so I did a cast right here to cast it, and then I did the same thing for B, and then I did this here. Okay, so if the age of A is less than the age of B, I return a negative number. If they're the same, I return a 0. Otherwise, I return a positive number, and then it all worked. So here's how I could make this a little bit simpler. Just go return AA pointer age minus AA pointer, sorry, BB pointer age. And that's all you got to do. So if the age of AA was greater than the age of BB, when you subtract them, you'll get a positive number. If they're the same, you'll get 0. And if the age of AA was less than BB's age, then you'll get a negative number. So all you have to do is subtract them. Oops, and we'll compile it again. Same results. And then here's the last thing, is let's say you want to reverse it, right? So that it sorts in reverse order. All you got to do is swap that. just subtract in the opposite order. And then they all get sorted in the opposite order. Okay, so this idea of passing in a function to another function allows us to make that original function, the qsort, really flexible, because it no longer has to know anything about the data it's actually sorting. All it has to know is, here's how many elements there are, here's how big each element is, here's the address of the array, and here's a function that's used to compare two elements. And then you, the programmer, provide that function because you know what the data is supposed to look like. Okay, so I hope that was a good introduction to how qsort works. I'm sorry I got a little slow there in the middle as I tried to get that sorting function to work. Maybe the next time I do a video about this, I'll have figured that out and I can just code it up very easily. But this is the way that the comparison function works, is you're given two pointers to two elements in the array, and then it's up to you to figure out how to actually compare them. You're probably going to have to do lots of casting back and forth from void pointer and so forth. So that's what I've got for tonight. I hope that was informative for you. I'll probably be doing more of these videos in the next couple of weeks. Then the semester will be over, we get a little break, and then we start again in January. So if there's any more questions, I'll try to answer them in the chat. For those of you on the video, I'll say goodbye for now, and I'll see you next time. Bye-bye.